Hi, everyone. Thank you for the opportunity of presenting this work in this very nice meeting. I will show you a model for Forbush degrees anisotropy and primary spectrum modulation based essentially on the global neutron monitor network. And this work has been done with Monica Lorenzo, with other co-authors, as you can see here. And as Matteo already said in the previous presentation, all the problems, scientific questions related to the modulation and to the transport of high energy particle by interplanetary structures, such as interplanetary color mass ejection, is related to the question number 3 of Spearhead. And in this work, I'll show you the modeling of primary spectrum and anisotropy with the aim of inferring information about low rigidity spectrum. So to extend, in some sense, also previous modeling towards sub-GeV energy range, and to observe how the global configuration of an ICME organizes the particle anisotropy during the magnetic flux drop passages. So this is, I will show you a case study for the first large Forbush degrees observed in the cycle 25, so November 4th, 2021. And it was a pretty nice event because also we had the chance to have measurements in at least two points in the heliosphere. Because solar orbiter was at that time very pretty aligned with the Earth, and we observed the same kind of CME structures both at solar orbiter at the Earth. And from the high energy particle perspective, what I will use in the analysis would be essentially the single count measurement from the C model inside the high energy telescope of solar orbiter by following the procedure previously illustrated in the Wolf Foster and co-workers in 2021 paper. And they showed also that the energy of the count rates of proton in single count is above approximately 12 MeV through GANT4 simulations. The Earth space-based point of view will be the high energy particle detector 01 on board the China Seismo electromagnetic satellite, which is an ionospheric satellite with a high energy particle detector on board, which measure electrons between 3 and 100 MeV and protons and heavier nuclei between 30 and 200 MeVs. So this is the heliospheric situation for this event. So we have solar orbiter at 0.85 AU, which was very pretty aligned with the Earth. And if we look at solar orbiter data, what we see is essentially a clear, typical ICME structure with shock sheet part, quite complex sheet part with substructures. And then we can identify with some let's say arbitrary borders, the last part of the very huge magnetic flux drop structure. And if we look at the plasma parameters, we see all the typical signatures. So very magnetized structures with low plasma beta, drop in the temperature and density. We clearly see from the EAS detector, so the electron sensor of solar orbiter, the bidirectional electron strahl inside the CME. And if we look at the percentage variation of the count rate intensity of the count rate, galactic cosmic ray count rate from HET telescope, what we see is a clear 2 steps Forbush degrees, reaching the deep with this very large plateau during the magnetic flux drop. So if we zoom out this figure, we can see that this Forbush degrees is something very tiny here. I just highlighted here the shock and the magnetic flux drop part, but we can see that before it was preceded by the very well-known GLE 73 on October 28, October 2021. So in order to be clean, to have a reliable estimate of the background, in order to compute the percentage variation of Forbush degrees, so the amplitude of the Forbush degrees, we will refer to some pre-GLE period, which is has been chosen on October 2023. So after some hours, the CME crossed the Earth. These are measurements from the wind spacecraft. You can see all the signatures, which are very, very similar to the one observed at the solar orbiter. We have also a comparison between all the plasma parameters, magnetic field, electrons, RAL, and cosmic rays observed in the Earth with these two last panels here. So the first, the middle panel here is essentially representing different count rates from the HEPD01 instrument with different energy thresholds. And we still see the clear double step decrease. And on the bottom panel, I'm showing here several neutron monitor observations. We can see that a clear decrease during the magnetic flux has been recorded, for instance, at South Pole with this flat dip, resembling the one that we observed in space. This more peaked is associated with Kerguelen, so southern hemisphere. Rome and Oulu are reported here because they are shifted, they reached a dip of the Forbush degrees at different times. And another polar station like Thule didn't see any variation during the magnetic flux. So at first glance, this gives us an idea of the anisotropy of this event. So in order to model the response of the neutron monitor to this perturbation, what we did is essentially we get inspired from the perspective of modeling the primary spectrum from a work by Ilya Usoskin, where he used as a guess for the spectral shape, the Gleason and Axford model. So we are just using this Gleason and Axford model, and in particular the modulation potential as a fit parameters for our spectrum. He found, for instance, on the Pamela 2006 Forbush decrease event, a very nice anti-correlation between the force of the modulation and the level of the count rate of the Oulu station. And regarding the anisotropy, since this event has been studied in several other papers, and it has been shown, for instance, by Munakata people that it is very, very anisotropic, and it shows a bidirectional anisotropy, we decided to use a spherical harmonics expansion in order to take into account this anisotropy factor up to the second order. So this is the model. So we have the anisotropy function, the initial, the guess for the primary energy spectrum, the coupling function of the neutron monitors, and this is the essentially what we set, what we fit on neutron monitor data. We measure the pre-event galactic cosmic ray background by using HEPD01 measurements. And we use this very awesome tool also provided by Oulu people to compute all the asymptotic directions as a function of time for all the neutron monitor station. And we use the Tsiganenko-01 model for the magnetospheric model, and the coupling function have been updated by using the Mishev 2020 updated yield function that are here reported in comparison with, for instance, the coupling function of Clem-Dorman 2000. And we can see that there is a significant difference, especially when we go towards low energies. So what about the ICME structures? I reconstructed the geometry of this CME by using the Grad-Shavranov method, which is a method that allows to retrieve, to infer quasi three-dimensional configuration of the ICME by exploiting a single spacecraft measurements. Here you can see the outcome of the method. So we have the axial magnetic field, and we can see these two traces, horizontal lines, which represent the wind spacecraft crossing the magnetic flux and also the solar orbiter spacecraft. In order to validate this kind of reconstruction, the only thing that we can do is essentially to extrapolate the magnetic field reconstructed through the Grasha-Franov method at the height of a different spacecraft with respect to the one used to get the reconstruction. In this case, we used wind to get the reconstruction, and we tested the rotation on the magnetic field, and so the goodness of the performed reconstruction by using solar orbiter measurements. As you can see here, but just a rough estimation of the time by assuming a constant velocity, we back time shifted the reconstruction profiles, which are these dots in this picture, and are essentially compared with the solar orbiter observation. You can see that the rotation on the large scale are pretty consistent. So results of the model, I am showing here the potential, the modulation potential phi as a function of time. You can see that, of course, it increases towards the minimum of the Forbush degrees. This square represents the 12-hour smoothed phi value of the phi, and it is essentially to synchronize this modulation potential retrieved by fitting neutron monitors data to the cadence that we have on HEPD01 for the differential proton fluxes. On the bottom panel, you can see the anisotropy, so the first and the total first and second order anisotropies from the spherical harmonics expansion, and you can see that the anisotropy turns off during the magnetic flux of passage, and it reaches its maximum, especially the A2 terms, which is dominating essentially the anisotropy, suggesting us that, of course, the anisotropy in this event is mostly bidirectional. So concerning the primary spectrum, this is a comparison between the outcome of the model, which is this orange line, compared to the HEPD01 measurements, which are these orange dots here. And the blue dots and line represent the initial fit and the background galactic cosmic rays. And you can see that we are pretty much in agreement with observation for this event. If we use the obtained value of the modulation potential to reconstruct the percentage variation during the Forbush degrees, at the maximum of the Forbush degrees, we can see that the flat trend that is observed from the data, you can see here a different value of the amplitude observed for different energy threshold on HEPD01, and this square here is a high energy telescope of solar orbiter. You can see that the model is pretty consistent with this observation, producing this nicely flat trend. So regarding the anisotropy, this is on this left of this slide. You can see the anisotropy that we get by fitting our model. By looking at the same event studied by Munakata people, we can see that we are pretty much in agreement. So we obtained at the same time the same result. I also plotted here on this line the parallel and anti-parallel direction with respect to the magnetic field, the interplanetary magnetic field with triangles, and also the parallel and the anti-parallel direction of the axis of the magnetic flux. As you can see, of course, this anisotropy is mostly driven by the geometry of the magnetic field, of the total interplanetary magnetic field, but it is important to notice that, of course, the angle between the magnetic flux axis and the interplanetary magnetic field is less than 40 degrees. So the axial component of the magnetic field is essentially significant during this event. And indeed, by looking at the ratio between the Larmor radius of particles with rigidity of 15 gigavolts and also to the magnetic field curvature estimated by computing this parameter right here, we can see that the values, especially during the crossing of the core of the magnetic flux are very, very low. So meaning that essentially the magnetic field is strongly affecting the particle's motion. So we are expecting that typical energies, effective energies of neutron monitors, we are observing an anisotropy which is organized by the interplanetary magnetic field. So in summary, we extended previous modeling, previous study of this event towards lower rigidities. We confirmed the bidirectional nature of the anisotropy observed, even though we can speculate a little bit on the difference in the force of the anisotropy that is observed from the parallel with respect to the anti-parallel direction. Indeed, when we look, for instance, to the model by Kritinadam and Ruffolo 2009, which essentially predict one unidirectional anisotropy of cosmic rays for drift orbits trapped inside the magnetic flux rope, we would expect, in our case, given the rotation of the colloidal field that we get from our reconstruction, increasing galactic cosmic ray flux exactly along the parallel direction with respect to the magnetic field. It is, of course, just speculation right now. It is something that need more study, more investigation in the future. And we also plan to fit this model on other events in the future. Thank you for your attention.